I think we can get started. Thanks everyone for joining us to discuss the third module so far of the V1 specifications, being consensus. We have Andrew and Daniel from the protocol team to discuss the consensus module with us. We'll be going through different aspects such as the consensus algorithm itself, how this new consensus module selects leaders, and how invalid transactions are handled by the consensus module. So we'll go through each of those in turn. I'll have Daniel and Andrew discuss in detail how those work in V0, how they work in V1, and what's improving with those changes. And then at the end of each sort of main section, we'll open it to questions. If you do have any questions at any time, please post them in the V1 research channel in Discord, or raise your hand in Discord by pressing the hand icon at the bottom of your screen, or you can do the same on Twitter, and we'll bridge that over here into Discord. So yeah, before we get started though, I just want to call out that today is the last day to apply to come to InfraCon. We have our first ever community conference taking place May 20th to 21st in Punta Cana. Yeah, the deadline for applications to come to that event is 5 p.m. Eastern today. So please, if you want to come, even if you think you're important enough that you'll get an invite anyway, please submit your application for that. It's going to be a lot of fun, and we're going to have a lot more of these types of discussions there across the whole spectrum, from protocol, V1, economics, governance, etc. So you're going to want to be there. So without any further ado, I think we can get started talking about consensus. So I think the first thing, unless either of you want to add anything else, I think the first thing that we should jump into is talking about the consensus algorithm itself. Specifically, though, for anyone who may not have as much sort of background knowledge on consensus, talking a little bit about Byzantine fault tolerance, BFT, and how that differs from Nakamoto consensus, which is what most people think of when they think of blockchains.
So I'll jump into that. And before we even answer that question, I think for those who have context and for those who don't, something important to mention is, why do we even need consensus in a blockchain? So we covered the utility module maybe a month ago now. And the utility module is really the core business logic, kind of the secret sauce that makes Pocket what Pocket is and brings utility to its developers. And then a couple of weeks ago, we covered the persistence module. And the persistence module is what we need in order to read and write to the state of the blockchain, maintain it, and also make it efficient for node runners to run their nodes and support the network. Now, what the consensus module is responsible for is not reading and writing to the state, but making sure that that state is consistent across a very large and permissionless network. So I don't actually know the exact number of nodes that we have on the network right now, but I believe we're pretty close to 40,000 at this point. And that is a permissionless network where any one of those nodes can fail at any point in time, or potentially be adversary, or what's called Byzantine, which means that it actively acts in an adversarial way to potentially bring down the network, or lie to its peers, or perform some sort of malicious action. So that's kind of the high level idea. And then jumping into Jack's question around Nakamoto consensus or Byzantine fault tolerance. BFT has been around for, the Byzantine generals problem has really been around for decades. and there have been a lot of different algorithms developed to solve this problem over the years. And the idea is very simple, that if you have a few different generals, or you have a few different nodes in the network, and you don't know which one of them is trustworthy, which one of them is faulty, which one of them is Byzantine or adversary, you still need to come to a consensus in some way as soon as possible. And through some proofs that we're not going to get into today, basically the theory shows that you can come to an agreement as long as more than 2/3 of the network agree on the same state. So what consensus does is make sure that at least 2/3 of the network agree on that state. And then we actually use the persistence module to store that state, and the peer-to-peer module, which we'll cover in the Q&A, to disseminate that state throughout the network. In contrast, Nakamoto consensus, which everyone is familiar with through Bitcoin, is a little different. Rather than having a leader in the network that kind of asks everyone or proposes a change in the state to the whole network, and then gets votes from the whole state, gets votes from the whole network on that new proposal, it's more probabilistic. So with BFT, we are able to achieve what's called deterministic and immediate finality, whereas with Bitcoin and Nakamoto consensus, it's non-deterministic finality, because we're always dependent on the longest chain, which can potentially change depending on how much work was put into that chain.
That's great. I'd like to summarize that with reference to the chain itself. So I'm going to attempt that, and you can correct me if I get it wrong. But essentially, a Nakamoto consensus, anyone can suggest a new block in the chain, and the winning chain essentially is the longest one, and that's how you end up with forks and so on. With BFT, before we can even add a block to the chain, we need 2/3 majority of the validators. So there's no possibility of having forks, having branching chains. We have only one chain, and we can only proceed with the chain if we have a 2/3 majority of validators saying yes, that's correct. If we don't, instead of a fork, what we get is a chain halt.
Yeah, that's correct. And then the only thing to add to that is that BFT algorithms are often leader-based. So through some mechanism, we elect a leader, and then 2/3 of the validator need to agree with what that leader proposed, and then the chain can make progress.
Yep. And could you elaborate a bit on why we use BFT instead of Nakamoto?
Yeah, so most proof of stake blockchains, or I believe, maybe it's incorrect to say, but I believe all proof of stake blockchains actually work with use BFT due to its immediate finality. Because when it comes to determining the stake or determining rewards or making sure that the data being disseminated is correct, we don't want to potentially have a longest chain that is forked and then the entire state changes at some future point in time. In order to guarantee that the quality of service of the nodes of the service is correct and the integrity of what the services are doing, we really want to have determinability that when a block is committed to the chain, it's there, everyone has agreed on it, and then the blockchain can move forward to the next one.
Right. There's a lot in our protocol, in the utility module, especially, that relies on using the current state of the blockchain to determine things like, for example, how when dispatching sessions, which service nodes should be matched with an application. And if you have different nodes with different versions of the state, then that's going to fall apart. So yeah, our protocol relies a lot on the current state, which is why we need only one version of the current state, essentially. So I think that's a good sort of background on BFT versus Nakamoto. One thing to clear up front is that we are changing our consensus algorithm, moving to V1, but ultimately we're still going to be using BFT. So keep that in mind. But before we talk about V1 BFT, I'd like to talk a little bit more about V0's BFT algorithm, which is known as Tendermint. And I'd like to specifically talk about the drawbacks of Tendermint as it relates to the expense of maintaining consensus, of communication between nodes, and voting on blocks. So perhaps we can dive into that, and maybe first we can talk about how gossip is structured in Tendermint.
Yeah, so let me jump into that. Firstly, when people refer to Tendermint and when I think about Tendermint, it's a very overloaded term in the sense that Tendermint BFT is a theoretical BFT algorithm. Then there's also the implementation of Tendermint, which theory often differs from the implementation once you get to the coding. And then there's also the Tendermint framework, which is part of the Cosmos SDK and is a modular framework used by many chains in the Cosmos ecosystem, and even those that are not. So it's a theoretical algorithm, it's an implementation of that algorithm, and then it's also a framework that is modular and used throughout the network. Now, the way that works right now is it has quadratic linear complexity. So if you have 10 nodes, it means that the number of messages that are required to be disseminated throughout the network is quadratically proportional to that number of nodes. And this is one of the big problems with Tendermint, that not only is the number of messages non-linear, so if you're reaching tens of thousands or hundreds of thousands of validators in your network, the complexity on and kind of the pressure on all of the nodes increases drastically. But it's also harder to understand and interpret. So if you look through the docs, Tendermint's been around since Tendermint BFT, I think, was originally conceived in 2016 or 2017. And there's a lot of gossiping throughout the network in terms of approvals and nil votes whenever a block is being disseminated. And this kind of creates a lot of CM load in terms of understanding what is actually being sent around the network and what consensus is being, which block consensus is being applied to. In contrast, actually, we'll get into V1 in a moment, right, Jack? Or should we jump to that right now?
I think we can move on to V1, but I just wanted to sort of provide some context on the effect of the expensiveness of Tendermint's communication complexity. So the majority of Tendermint chains have far less validators than Pocket has. We're talking hundreds, and the reason. So we had to essentially separate validators from servicers, limiting the number of validators that the network has to 1,000, in part because of these limitations of Tendermint. It's not an issue that other networks have because they keep the validator set small. They keep it a couple of hundreds. Pocket has different objectives, and we want to have a massive network of nodes. So we've had to, in V0, we've had to implement changes like the validator servicer separation to get around those limits. But with V1, we would be looking to actually fundamentally re-architecture consensus so that we're not working with those limits. So with that, I think we can talk a little bit more about V1 and HotPocket.
So just to add to what Jack said and to add some timelines in there. So Tendermint, I believe, was written in 2016. 2018 is when it really started getting some adoption. And around 2020 is when Pocket forked Tendermint in order to be used as part of the core Pocket protocol. And if you look through a Tendermint documentation, it literally, there's a little note or a warning that says the number of validators is kept at 10,000. And because of the communication complexity, you can't exceed that. So as kind of the crypto industry grows, and especially as the Pocket network grows, the larger the network is, and the larger proportion of the network that can be validators, the more trustworthy and the more permissionless the network can be. So if you can imagine, in a few years, let's say there's a million nodes on the network, and all of them are permissionless and participating in consensus. That is a very robust network that you can trust, that's going to be difficult to attack unless you have a ton of resources. So that is, and then one of the things that happened recently, since we're still on V0 of Pocket, is originally anyone who's a servicer was also a validator, but that didn't scale. So now we have almost 40,000 nodes and servicers on the network, but the number of validators is capped to 1,000 based on your stake. So that is kind of one of the big other reasons why we're moving away from Tendermint. Before I jump into HotPocket, another thing to note is that when Tendermint was first developed, it was developed as a modular framework, and modularity kind of is a double-edged sword in the sense that it's good in some cases and it's not good in others. So it's good when you just want to get started quickly and build a blockchain on top of it. But when you really know what you're building and you really want to optimize for a specific use case, that's when application-specific monolithic repos can actually be much more beneficial from an end-to-end integration point of view. And that's why V1 came about at all. So with V1, we're using an algorithm called HotStuff. It's a leader-based Byzantine fault-tolerant state machine replication consensus algorithm. And it was originally developed by the Facebook Libra/DM project. And we're basically using it, implementing it, and adapting it to our own needs. One of the big benefits of HotStuff is, number one, it's linear complexity. So the number of messages, the number of messages that you need to send to achieve consensus is linearly proportional to the number of validators. So if we want to scale to hundreds of thousands or millions of validator nodes, that is actually going to be feasible and practical. And secondly, it's also much easier, at least in my opinion, or if you look at the documents, to understand. So a key piece, this is where kind of theory also differs from implementation. There's the theoretical understanding, and both Tendermint BFT and HotStuff BFT can be understood at a high level. But then when you look at the design architectures and you actually try to implement them, HotStuff is also much easier to understand end-to-end and implement. And if you look at some of the other blockchains that are coming out today, so HotStuff, the white paper was originally released in 2019, and today I'm learning that the Flow blockchain is using it. The new Facebook spinoff blockchain is using it. There's a couple others, including Espresso Systems. So HotStuff is really becoming the state-of-the-art BFT algorithm to adopt, and there's different variations of it. And at Pocket, our variation is called HotPocket. And kind of what we're going to be doing is making use of the basic hot stuff version of hot stuff. Is just one of the variations. And the key piece that we're modifying in there is the leader election. So if you look, this is actually a good opportunity to jump back into how leader election works in Tendermint. The original Tendermint algorithm and Tendermint codebase implements leader election in a very deterministic approach. So you have 10 leaders and you just rotate, as long as they all stay online, you just rotate through them one by one. One of the reasons Pocket forked Tendermint a couple of years ago was to have random round robin leader election. So rather than keeping it deterministic, you select a random leader on every single round. With V1, what we're doing for leader election is adopting Algorand's VRF CDF approach, which means that we're using verifiably random functions and then using a cumulative distribution function in order to pseudo-randomly select a leader in proportion to how much stake they have in the network. I'm going to stop there, Jack. What should I jump into more, or do you have any questions?
Yeah. So leader selection was the next section. So we've slightly jumped forward a bit, but I understand that like all of this fits together. So it's important to try and get a full picture of how it all works. Did we cover how? Did we cover the progress on voting? How Tendermint is pessimistic and hot stuff is optimistic?
No, that's a good point. So, okay, before we jump deeper into leader election, one important innovation that HotStuff brought about is what's called optimistic responsiveness. And if you break down optimistic and responsiveness into two, optimistic simply means that the blockchain can start making progress as soon as you have 2/3 of the network agreeing on a certain state. So the validator has a proposal, 2/3 of the network votes on that proposal, and so that's optimistic because we don't need the other third, whether or not they're trustworthy, to vote on that proposal. Responsiveness simply means that as soon as we get those, we don't have to wait for a specific delay. So if we get those in 1 nanosecond, we can keep going to the next round or to the next step. If it takes 10 seconds to get them, then that is the delay that we have. That there are built-in mechanisms called a pacemaker to make sure that we never wait indefinitely in case there's a network partition or some other issue. On the other hand, with Tendermint, even though it was optimistic that you only needed 2/3 of the network to vote on something, it was not responsive in the sense that even once you get those 2/3 votes, you still have to wait for a predetermined amount of time before progressing to the next step. So this is actually one of the other big benefits that HotStuff brought about and that HotPocket is adopting.
I think it's important to explain how this is achieved, which is through the introduction of a new phase in the voting process. So, as I understand it, the reason why in Tendermint you have to wait until everyone has voted is you have no way of distinguishing between of identifying whether a validator is actually present for the vote. So in Hot Stuff, we introduce a new phase in the voting process where a validator actually has to signal that it's present, that it's aware of the vote taking place, and then if it doesn't do so, in the next phase, which is the voting phase that we already know from Tendermint, those validators are essentially excluded from the quorum requirement. So we only have to wait until those that are present have voted with 67% majority. Is that, have I explained that correctly?
Yeah, that's kind of correct. So one of the big things is that in Tendermint, we disseminate both nil votes and approval votes throughout the network. So you need to wait for both of them before you actually move on to the next step. With Hot Stuff, one of the other things that it introduces is dependent on something called quorum certificates. So it doesn't actually need 2/3 signatures from the entire network in order to make progress. What the leader does, or what it's responsible for, is aggregating those signatures from 2/3 of the network, kind of combining it into one, and then sending it out to the rest of the network. So if you're if you're not a leader, but if you're a replica in some round and you're receiving a quorum certificate, you know by definition that at least 2/3 of the network has voted with approval on that specific block, and that's how you
And
can
the,
move further optimistically.
and the leader that you're referencing there who aggregates those certificates, is that the listener?
Yeah, the leader is the listener, and for every single round or every single view change, the leader is the one who is responsible for taking partial signatures from at least 2/3 of the network, aggregating them, and then sending it out to the entire network.
Okay, I think it's important to bring that back to your earlier point about how hot stuff is linearly complex, as opposed to Tendermint being quadratically complex. And the reason for that is we have those, instead of nodes having to communicate with everyone, we have specially selected listeners or leaders who listen for messages and then broadcast them out to everyone else. Combining that with the introduction of this phase that allows us to exclude validators who are just simply not present, then we have a much more structured, linearly complex, and optimistic process for achieving consensus.
So if we even take the stage as a very simple example, if Andrew is our leader for a certain round, and you and I need to create partial signatures, rather than me needing to send a partial signature to both Andrew and you, I'd only send it to Andrew. You would only send it to Andrew. He'd aggregate it into a quorum certificate and then broadcast it back to us in a linear fashion. So what this does is it's faster, it's simpler, it creates less messages being disseminated throughout the network, and it lets us progress optimistically or responsibly.
Yeah. And then the last component of it is the pacemaker module, which helps to ensure that we have reliable block times, which are all the same time. And does that act in both ways, so that even if the block could be completed faster, that it will still stay to the standard block time?
Yes. Ultimately, with a pacemaker allows us to have the optionality to control the speed of consensus. The process of consensus always should go as quickly as possible. Now, when that information is disseminated and how the parameters are adjusted is up to the validators and the protocol that the validators agree upon. So that's generally the premise of the pacemaker. You can ultimately think about Pocket Network's history, it's how it's dealt with Tendermint and chain halts in the past, and how with Tendermint, which has a and I'm using this word as a computer science term, not a diss, but a naive pacemaker, where you just simply you just simply increase the timeout until the votes will theoretically clash, or the validators timings will theoretically clash, so that you can have an aggregation of those votes and thus move on to the next round. A more sophisticated pacemaker, as specified in the DM protocol, for example, which is what Pocket gets a lot of inspiration, HotPocket gets a lot of inspiration from, will actually allow you to have communication between the validators in order to bypass these kind of relatively unsophisticated theoretical algorithms that will truly work just in an indefinite amount of time. We've seen in the past, sometimes it takes even though all the validators are online, it can take the validators 72 hours for their votes just to collide. And that was with, the amount of validators we had at the time. If we're talking about hundreds of thousands, you can imagine a much more sophisticated pacemaker modules is required out of this protocol, and that's kind of what we are aspiring to do here. So when you combine the properties of linear complexity plus optimistic responsiveness plus in a more sophisticated pacemaker, you just have all of this optionality to play with in terms of protections against more sophisticated attacks, in terms of, or in addition to getting the consensus to where it needs to be so that we can serve the utility. Because one thing that was touched on a little bit earlier is that Byzantine fault tolerance and immediate finality of consensus is ultimately a means to an end to ensure that service nodes rely on the same state for the decentralized applications. Everything is a means to an end here so that we can provide the best Web3 infrastructure. So if you combine these elements that Olshansky or Daniel has described up to this point, you can start to imagine how this consensus algorithm might be magnitudes greater than what we have today.
So in terms of implications for the utility module and ultimately the service that we're providing, these innovations in the consensus module essentially ensure that consensus will never be a bottleneck on the service in terms of expense for the network. And then with the pacemaker, gives us flexibility to adjust block times as needed for the benefit of the service.
That's correct. I mean, ensure is a strong word, but what it does is it provides more guarantees for
Yeah.
us in terms of optionality. Because right now, ultimately there is in V0 there is a bottleneck in consensus that forced the separation of validation and servicing. That decision is one that shouldn't be mandated by technological bottlenecks rather than DAO and community involvement and just general thought about what's the best way to serve, the utility, not ultimately, Tendermint isn't optimized for XYZ. So we are forced to, at a utility level, split the servicers and validators.
Yeah. So just to add to that, if the community decides that we want to cap the number of validators to some degree, that is a reasonable approach that can be discussed, but the consensus protocol shouldn't limit the number of validators that we can have. Similarly, if we want to have 5-minute block times, that could be a parameter that the community can agree on, but the consensus protocol shouldn't limit how quick or long block time should be. So in reality, it maintains all optionality in terms of scalability, permissionless, and speed. And then depending on the utility, we can customize it as need be.
Awesome. I think we've covered everything we need to. I think for the consensus algorithm, that was the meatiest part of the Q&A. So there's probably a lot to digest there. Sorry for these notification noises. So I want to open it up to the floor and let anyone ask any questions they might have about all those topics we just discussed. Remember, if you have a question, you can either raise your hand in Discord or Twitter, or if you prefer to type, you can use the V1 research channel in Discord. So we have a question here from Addison.
Hello.
Hey.
So I don't know if you guys can, I can't hear you, Jack, but my question is, the docs say that validators will check transactions in the mempool. They'll check them against the current state to check for validity. So right now what I do is I'll send like multiple transactions. I'll send a transaction at the time of sending that's invalid, but I will be transferring funds like into a wallet, for example, and then out of that wallet in that invalid transaction. would that not work in V1?
So no, that'll totally work in V1. It's that what you're really talking about is the FIFO mempool design, right? First in, first out. If you're sending, if you're going to send a transaction that's invalid if no other transactions went before it, that is ultimately just the first in, first out properties of Tendermint. And ultimately, as specified right now in V1, we are maintaining that property. However, in terms of validation of transactions, Jack, correct me if I'm wrong. I think we have a section dedicated just to that at the end of the talk. And we should dive into that more because there's a whole lot of improvements on top of the life cycle of transactions. But for your specific question, Addison, there's no difference, right? When you do something like that, just an FYI to the community, there's no guarantee theoretically that your transaction is going to succeed. It just probabilistically will because the transaction is gossiped quicker than the other the dependent transaction is gossiped after the transaction it depends on, and that's how it's received, and you're able to perform that. I guess you can call it multiple dependent transactions in a single block. However, in a world where there are internet faults and issues with clients and things like that, those transactions are not guaranteed to succeed based on the consensus algorithm of Tendermint today and V1 tomorrow, right? But yeah, no difference from that. You can keep doing it. I've done it several times. I just wanted everyone to know that it's certainly not a guarantee that those will pass. It's just when you think about the speed of light, you think about transactions getting from A to B. Yeah, it's probably going to work 99% of the time.
Okay, cool. And also, are you expecting the block times to stay the same? And what about the block sizes as well?
So block sizes should hopefully go down. That's more on the utility module than anything. Block times is really a discussion for later because we need to benchmark HotPocket and see what the capabilities are, get that information out to the community, and allow them to make the decision. In my view, Pocket Network is not meant to be purely transactional. It's supposed to be a utilitarian. If we have the ability to, and of course, when you have more blocks, quicker blocks, you have more block headers and more blockchain overhead. Slower block times are beneficial in the way where it might better serve a utility where you're having these hour-long sessions and same amount of transactions but less overhead, right? However, on the flip side, if Pocket Network community deems it more transactional for whatever reason, there might be more of a user experience benefit to have quicker block times. But there's not something where we've set out in the specifications today where we're like, yes, we're keeping the same block times, or no, we're not. Ultimately, the original block time was chosen because it discourages people from using Pocket from a just purely transactional nature, because ultimately it's so fitting currently these 15-minute block times to allow for the utility to ensure a smaller blockchain and to promote the ethos behind the Web3 infrastructure provisioning, which is ultimately the vision, right?
Yeah, cool.
Yeah. The only thing I'll add to what Andrew said is some of the other blockchains that do use hot stuff are advertising single-digit second blocks. So with HotPocket, what it's going to do is enable us to have as quick block times as we need or as we want or as the community deems necessary. But for example, taking utility into consideration, one of the most important pieces is also having on-chain quality of service data for our servicers. So it'll really be up to a discussion to decide how much time do we want to appropriate per block to test the servicers to decide what their score or grade should be for that specific block time. Because ultimately, making sure that relays are as fast as possible is the key, is the most important piece to Pocket.
Cool. That makes sense.
Thanks.
That's
Any
all.
other follow-up?
Guys.
Awesome. Thank you. We have a couple of questions in the chat as well. So from Pickpocket, we had more of a general consensus question. How do nodes know whether or not a proposed state is an attack or is legitimate? In other words, how do good actors know which way to cast their own vote? What are the ways that nodes can detect bad actor blocks?
Yeah, so this is a good question. Because the assumption of blockchains is that each individual node provider, or node runner, if you will have a copy of the software that represents the state machine that they democratically believe is the protocol. They can make their own decisions based on that software. The software automatically do it. What this looks like is, if everyone on the stage has a Pocket Core client or a Pocket V1 client, whatever you want to say, our softwares should automatically vote correctly based on the state. Meaning, if Olshansky is a malicious proposer or leader, if you will, and he wants to double spend his own funds, he'll come up and say, I'm actually sending 30 Pocket to, Node Pilot over here, and but I only have 15 Pocket in the state machine, right? Well, what should happen is Jack's software should say, hey, I'm going to throw an error because he has insufficient funds. And Andrew's software should do the same, right? Regardless if it's coded in Go or Python or Java, like it doesn't matter. The state machine we democratically agree upon as a decentralized society are those protocol rules, right? So when I cast my vote as a validator, it's going to purely be based on those set of rules that are agreed upon by the participants that are the validators. That's why being a validator in any blockchain network is incredibly important, right? So ultimately, using the rules that I believe true, I'm able to cast my vote independently of Jack or Olshansky. And if there was a malicious player that was able to take over 33% of the network, they could ultimately cause a chain halt because their rules might disagree from the actual protocol rules or the ethos that the other 2/3 support, right? And if they are able to take over 2/3, you can actually commit blocks. This is very similar to a 51% attack in Bitcoin. I think I covered the question, but Pickpocket, you can follow up if you have any more.
We have a follow-up. What about something like a parameter change transaction where there's no history to look back upon?
No matter what the transaction is, if it's a valid transaction, it will have a handler. Okay. So let's say, the ACL owner of parameter blocks per session wants to make the blocks per session 1,000. Okay. Which means we now have 1,000 block sessions. That's a long time. Maybe the DAO a long time ago, or the developers of the protocol, architects of the protocol a long time ago decided, hey, the maximum value for the blocks per session parameter should be no more than 25. Okay. And that's in everyone's version 1.0.0 Golang software, that parameter value is just not going to work, right? So when that parameter value comes through and he tries to say, hey, blocks per session is 1,000, my software is going to be like, no, that's invalid. That's an invalid transaction. And we're going to get to this in a little bit, but invalid transactions in V1 aren't allowed. So thus, this is an invalid block. I'm going to vote no on this proposal block, and I'm not going to change my state based on this block. Okay. So it's not always about history. A lot of times it's always about protocol rules and the state machine that powers the utilitarian economy that everyone's kind of following.
And I think to add to that, I think this is the importance of also having being able to build a consensus algorithm that has an unbounded number of validators in a permissionless network. Because if you fork Pocket 1.0 and you modify the logic for what a valid or invalid transaction is, and you decide that a valid transaction is something that only sends funds to NodePilot, for example, and you get 2/3 of the network to start running that software, then arguably the only definition of a valid transaction would be funds that are being sent to NodePilot. And this is where a permissionless network that's as large as possible actually gets its power.
Okay, we have another question here. Will the launch of V1 have a cap on the number of validators, or will all stake nodes be validators at launch?
That also, unfortunately, doesn't have an answer at this point. Theoretically, everything will always need a cap, especially when you get to numbers in int64. But it needs to be benchmarked to ensure that we have these guardrails in place, that we don't overestimate scalability, because we've seen in the history of Pocket sometimes explosive growth in the number of validators. I mean, we're close to 40K now, and if you go a few recordings back, you'll know what I'm talking about. So ultimately, I can't give you a clear answer, but it won't really be decided by us. What will happen is the protocol team will put out a report to the public and the community will have to make an informed decision and cast their own votes through representation in the DAO to say whether or not the max validators should be set to, max int64, which is essentially unlimited, or whether it should be set, to 1,000, etc. But ultimately, it's something that needs to be a decision that needs to be made when the data is given to or when there's an informed consent among the community.
Okay. Okay. We did have another question. It's been deleted. So, there's someone typing. I'll give it some time for that to come through. No hands raised either. Okay, the other question here is, so it was mentioned that the size of someone's stake will be a factor in being selected as a block proposer. Why does this matter? Why is it important to have stake amount be a factor? If there are 40,000 validators, why does the amount matter?
Yeah, so there's a difference between being just a validator and then a leader. So with every single round, you can there's one leader, and then all the validator replicas kind of vote on that proposal. Now, with original Tendermint, it was a deterministic loop through all the validators that are available. When we forked it, it was round robin selection, and with V1, kind of the attack that we're trying to prevent is a leader grinding attack. So depending on your stake, the higher your stake is, the larger is the probability that you'll be selected as a leader for that specific round, and also potentially earn the reward for being a block proposer for that specific round. But it doesn't guarantee that just because you have more stake, you'll always be selected to be a leader. So what we want to do is, through the pseudo random selection, prevent the ability from the network from figuring out who the leader is going to be for the next view change through verifiably random functions. And then what the CDF does is simply guarantee that the proportion of times you're selected as a leader is proportional to the amount of stake that you have. So the higher your stake is, the more rewards you can earn as a proposer. However, it's impossible to predict who the leader is going to be, and then in turn attack that leader to bring them down in the network. And that's how you can prevent chain halts and make sure it makes progress.
Just to dig into the why a little bit more, like why do proof of stake networks work this way? You know, ultimately the general premise is two things. Okay, premise A is if one vote got you, like, let's say no matter what your stake is, you just get one vote. Well, you can get more votes just by staking more, right? So there's a consolidation piece to it. It's like, okay, no matter what happens in a permissionless network, more money gets you more votes. That's just proof of stake, plain and simple. Now, why does more money get you more votes in proof of stake? Well, the idea is that the collateral that you have as a staker when you have more money is higher, meaning you have more to lose. You have more at stake, right? So ultimately, when you perform, if you perform malicious or Byzantine or faulty behavior that results in a burn or a slash, instances of this include double signing or not signing or long range attacks, things like this, or not proposing. This will result in a burn proportional to your stake. Thus, the assumption that is made in proof of stake, and I'm just talking generically, I'm not even talking about Pocket Network, is that the more you have to lose, or the more stake you have in the network, the more you want to operate within the bounds of that system and in that protocol, such that you'll be a good player, a good actor, because you want the system to succeed. Because theoretically, if you're sinking a lot of money into the system, which is generally things that people care about, you will be promoting that system. And thus, you wouldn't want to see it fail, or you wouldn't want to hurt your own interests in by doing something malicious. So I think that explains the why just a little bit better, in conjunction with Olshansky's security arguments about how the CDF and the VRF are playing into this selection, and how that balances out the interests of the democratic process with the capitalistic intention.
So just to clarify there, the reward that you are eligible for proposing a block will be proportional to the size of your stake as a validator. Is your odds of being selected to propose a block also proportional, or is that independent?
It's the other way around. It's your
Right.
odds are proportional being selected based on your stake, and then the reward is just based on the contents of the block.
Right. So statistically, over time, your rewards will be proportional to your stake. Makes
Yes.
sense. Awesome. So we actually thanks for that question, Shane, because you've segued us nicely into the next key area, and we've already covered most of it with that answer. I wanted to dig a bit deeper into some of these sort of terms that were mentioned in that explanation. We're with V1, we're moving away from round robin leader selection towards a blind pseudo random leader selection. So I'd like to maybe have like a explain like in 5 explanation of how V1 selection is different from round robin. What exactly is a verifiable random function? How is this being combined with the cumulative distribution function? And what are the implications of using those methods?
All right. So yeah, so in round robin random selection, we pretty much, you can imagine a tournament and you go in a circle and you pretty much guarantee that every single validator gets selected sooner or later in some sort of order. In VRFs with cumulative distribution functions, So a lot of people here have probably heard of digital signatures. You have your private key. You can use your private key to sign some sort of message, and then using the corresponding public key associated with it, you can verify that message. What verifiable random functions do for you is instead of just providing one digital signature, they provide two outputs. They provide essentially the equivalent of the digital signature, the hash, and then the output. And then the output is, so the hash is what you use for verification to really guarantee who signed what. And then the output is what you use in the CDF. It's essentially a number that you normalize to a value between 0 and 1. And this is what is going to govern the probability of you being selected. So with the cumulative distribution function, what we need to know is kind of what your stake is and what the total amount of stake in the network is. And using this random value between 0 and 1 in conjunction with knowing what your stake is as a function of the entire stake in the network is how we bias towards selecting a certain validator as a leader in proportion to their stake. And this actually also touches on kind of the answer Andrew gave earlier. He kind of explained why we do this, and without using the words, is a civil attack. So what this in V0, especially when every single validator was also a servicer, you always had kind of the incentive of running as many validators / servicers as possible, and you have an equal probability of being selected as that validator. With V1, if you want to be selected as a validator, there's really no advantage to running many different validators that only cost you more in resources, as opposed to running one validator with a higher stake as a single owner of those funds.
So the VRF, sorry, go ahead, Andrew.
Yeah, something that will help kind of clarify VRFs versus digital signatures is malleable output. So believe it or not, most digital signature algorithms can actually produce different outputs that are valid signatures, right? VRFs, well, let me touch on that a little more. What does that mean? That means if I sign some arbitrary bytes, the output will show up as a valid signature when verified against my public key. But if I use a Python client with the same key, like let's say ED25519 public and private key pairs, the actual signature bytes can be different, right? VRFs are guaranteed non-malleable in that you will always have the same output regardless of the implementation. This guarantee is incredibly important when you're basing things off of this off of consensus, and ultimately, it's not just about, hey, is this a valid signature? It's, can we use this output that comes out of this VRF for consensus and computation that will allow us to do something as important as select the leader in this system, right? So I just wanted to clarify that difference, because at face value, they're very similar, right? Because you still use a public key to verify the output, but that non-malleable output is really the key, because that, getting the deterministic output is incredibly important for the CDF function, which ultimately results in the leader selection for V1. And just a little background about the combination of these two. This is the project that actually pioneered this idea. Believe it or not, it's not Pocket. It's Algorand. They've been operating off this with their sortition, which allows them to have these non-grindable, non-malleable VRF or leader selections that promote, maybe for the first time that I've seen, unpredictability with very little to impossible chance of grinding.
And would I be right in saying the deterministic output of the VRF means it's also cheaper computationally?
As opposed to what?
So it's my understanding that the benefit of the VRF is also is that it's pseudo-random before the block is produced, but once the block is actually produced, it's still cheaper than an approach that would not have a deterministic output.
Yes, I think it would be cheaper. I think you're correct. But what I always focus on is that security aspect.
Right.
When it comes to, when it comes to language agnostic clients and things of that nature. It's just a more surefire cryptographic approach to having these guarantees that are required for something like this.
Right.
Yeah,
I
then
think
I
we can
haven't.
move on to the next topic, but you want to make another point there, Daniel? Go ahead.
Yeah, I was going to say I haven't actually looked at the benchmarking of VRFs versus other digital signatures, so I don't know if there is a computational benefit of one over the other. But it is worth mentioning that there is a kind of a network or consensus overhead that comes with VRFs because it's not going to be a persistent private public key pair that stays with the node, but in fact, we're going to rotate the VRF keys that each validator has periodically. So this is going to be a governance parameter, and every few blocks or every few sessions, we will need to cycle the VRFs the VRF keys that every single validator has in order to guarantee the security of the network.
Seems like a worthwhile trade-off. So unless there's any other questions there in the chat or by raising your hand, I think we move on to the last subject. We are over time, so I want to be conscious of that. The last subject is at the moment with Tendermint, Tendermint does not allow block proposers to first filter out transactions by validate or invalid transactions. And V1 will actually allow block proposers to validate their transactions against the mempool and then filter them out from the block.
That's correct. So Tendermint has, okay, so credit where credit's due for the Tendermint developers. They pioneered a ton of really cool technology, and unfortunately, they were operating under constraints that Pocket Network is not, or the Pocket developers are not, which is that they wanted to develop a consensus engine for an agnostic ABCI application. What does this mean? What are the impacts of that? What this means is the Tendermint team ultimately didn't want to make too many assumptions about how the ABCI application would act in terms of its purpose, its utility, even maybe its consensus or its Sybil resistant algorithm. You can still do interesting proof of work algorithms on top of BFT, believe it or not. So proof of stake is not your only option. But the what I'm trying to get at is, they have this separation between the ABCI application and ultimately the validation of transactions and the consensus engine itself. And a long time ago, back when they were developing the ABCI lifecycle, they made a trade-off. That's how I'll put it. It's a trade-off where they said, one beneficial design that we could adopt for our life cycle is for when transactions come in, don't validate them until the block is committed. And when the block is committed, simply don't save them in the state. They will just not affect the state. And this has a benefit because we didn't have to pre-validate the transactions before proposing or at any phase of the life cycle of the block until we determined the app hash that we were going to develop on or going to validate on. So this kind of optimization, if you will, comes at a more long-term cost as we see it. The reason why is because they're correct. It does not. They do not have to. A proposer does not have to validate a block before sending it out, and it doesn't. There's no way to do that in the Cosmos SDK or Tendermint as it exists today. And the transactions don't affect the state. They were correct in that in those realms. However, it does live in the transaction indexer, and it does live in the block data, which is the block store DB. So not the app state DB, but the block store DB and the transaction indexer DB, which ultimately you could say is not part of the blockchain, but in a real effect, it is, because you have to have those things, especially for an ABC app like Pocket Network, to validate transactions and to have the full copy of a queryable blockchain, right? An archival, if you will. So so why can't we modify Tendermint to have this new feature where it's going to pre-validate before submitting blocks and not allow invalid transactions as replicas? Well, the problem is the way that it's been designed in the relationship between the ABCI application, i.e. Pocket or Cosmos SDK, and Tendermint, and how they are a separation of concerns. If it was all one code base, this might be more feasible because you could easily maneuver pieces of code to and from different modules. But because they're separate and they were designed from the ground up as separate entities, rightfully so, if I will say, because of their purpose, it is not feasible for us to really do this without a huge, ultimately ground up overhaul of Tendermint, right? And what this results in terms of our thinking when it comes to porting over any pieces of Tendermint BFT is that we just need to build it from the ground up with the piece that is called the blockchain reactor, which enables this sort of transaction lifecycle, getting from the person who created the transaction ultimately into finality, right? So the way that we are handling it in V1 is completely different, and it's actually very similar to a lot of blockchains that you might recognize, like Ethereum or Bitcoin or any Nakamoto consensus, where we simply do not allow invalid transactions in proposed blocks. If you send a invalid transaction in a proposed block in V1, it will get rejected, the entire block, not just the single transaction, but the entire block, because the assumption is that the proposer is doing a service to the network and is getting compensation for that service by the network in the form of a block reward. And the service that they're providing should include the pre-validation, such that the rest of the blockchain and the rest of the network doesn't have to bear the burden of validating these transactions that may or may not be valid. Now, that wording's very like, re-examine that wording, because replicas always need to validate transactions no matter what. But having to validate transactions that are ultimately going to be invalid and still include that into your data directory is something that we at Pocket Network consider an unacceptable trade-off. And ultimately, it is contributing quite heavily to the disk size that we see today, the disk size requirements that we see today for Pocket Core, and a lot of the computational overhead that exists when processing a block, things that are centered or in the center of the problems that exist currently with V0. So what we do in V1 is, by having the proposer pre-validate and sending out this block, which is minimally or which is reduced to the minimum valid transactions that exist in a mempool, we are able to cut down on blockchain size. We're able to cut down on the block processing times, and ultimately have simpler validation rules for blocks. It's pretty simple to say, hey, if this transaction's invalid, toss the block. It's not a good proposer. Let's move on to the next step of hot stuff or new round of hot stuff, if you will, as opposed to, okay, this one's invalid, but it's invalid for this reason, and we'll include it in the transaction indexer and the block DB, but we're not going to include it in the state DB. You can see how this trade-off of not having real-time computation for a real-time computation during the block processing in consensus for a utility-specific chain like Pocket Network could be seen as unsavory. And that's why ultimately for V1, we have just completely changed directions and said, hey, we understand why Tendermint did this for their specific use case, but you'll hear this theme a lot. It's not the right tool for the job for V1, so we need to pivot. Jack, let me know if I said anything else, or if there's anything I need to dive into more.
I'm not sure that there is. That was a really in-depth explanation. I think just to sort of take it back to the consequences of this change, what this means is blocks are going to be less bloated because there'll be less noise, less invalid transactions being included, and ultimately it will be easier to index transactions as well, which for tooling like Pocket Scan will make life easier as well. Is that correct?
Those are good consequences of these actions, yes.
Awesome. So I don't think there was anything else that I wanted to sort of dive into with that subject. It's pretty straightforward, and I don't see why anyone would be opposed to those changes. Does anyone have any questions? You can raise your hand or type in the chat. Does anyone have any broader questions about everything that we've discussed on the call? Nope, I don't think so. Okay, I think we're done. Yeah, at this point, I would want to remind everyone that V1, the reason we do these calls is that the goal of V1 is to have the R&D process of the future of Pocket be opened up to the community. We have Discord channels dedicated to V1. We have open source GitHub repos. We have the forum open for anyone to share ideas and discuss all of the topics that we're talking about, to be involved in the ideation process of V1. I recommend reading the documentation. We have let me post a link to the channel in case anyone is new here. We have explainers here at this link that I just posted in V1 Research channel. These will go over all of the 4 modules that are in V1 in a sort of as layman as we can possibly get these topics without losing their meaning. And then at the bottom of these pages, you can go to the more detailed technical specifications that the protocol team are working from as they're building out this new code base. So yeah, I recommend reviewing the explainers first, then you can dive deeper into the technical specifications. And then when you've gone through all that, if you have any questions, feel free to post those questions in Discord or in the forum. If you have any suggestions, feel free to contribute there with GitHub issues or forum posts or whatever. And yeah, we're all very excited to get the community's input on this. Speaking of which, if you prefer face-to-face discussion and want to provide feedback or talk more about these topics in person, then you'll need to come to InfraCon, which is in Punta Cana in May 20 to 21st this year. Today is the last day to apply to attend. Post a link here in the chat as well, and the V1 Research channel. Please, if you want to come to the conference, submit your application by 5 p.m. Eastern today. But yeah, I think with that, unless anyone has any last minute, well, actually, if you have last minute questions, post them in the chat, and we'll answer them asynchronously. But yeah, thank you very much for attending, everyone. Oh wait, Daniel wants to add something as well.
Yeah, just to add to what Jack said about community contribution, we are, as the core team, taking it very seriously in V1, and that comes from having better documentation, having better tooling. So if you want to contribute through visualizations or improving the documentation or commenting on the protocol in theory or in implementation or adding tests for different edge cases in any one of the modules, please do check it out. And yeah, that's it.
Yeah, any and all contributions are welcome. You don't have to, you don't have to find a critical bug or submit a major feature for that contribution to be valued. Anything else you guys want to add?
Nope. Thank you, Jack.
Thanks everyone for joining. We'll see you guys in the next one 2 weeks from now, peer to peer.